This is, as Willie says, a novel lecture, so hopefully it's going to go okay. We hope to get it done in an hour. We will get it done in an hour, but hopefully we'll have plenty of time. So Kate, who's 9, is going to give me a hand, do some of the demos. And I suppose, so she's wearing her lab coat, as all good scientists should. So what's the context of this talk? So we're going to be giving this as a full day program in the Dublin City of Science in later this summer. So Dublin is the European City of Science this year. And there's a program of public engagement activities of which this will be one. And obviously it's not going to be an hour, it's going to be a full day. And so the kids will actually get to physically do all of the things I'm going to talk about. And so tonight I'm going to give you a taster for what we're doing. You should all have an evaluation. If you could complete those, that'd be great. If you don't have one, we can make sure you get one by the end. But please don't go before handing at least some of them in. So this is, a lot of what I'm going to do today is inspired by the Computer Science Unplugged series, which is a sort of a free-to-use set of activities for teaching computer science to kids between the ages of 8 and 12. There's a second part of this which I'm not going to do tonight, which is aimed at kids between the ages of 14 and 18. So what's computer science? So Willie gave a good shot at what it is. I suppose really it's about solving problems with computers, and that's a very informal definition. And of course, you all see cartoons and TV programs and animations online and on your TV screens. And behind these are some really interesting challenges that we solve with computer science. Now, what are we going to be talking about tonight? Well, I'm first of all going to tell you that computer science is important, and it's important both economically, so this is a piece for the adults, I guess, and intellectually. And then I'm going to try and go through 6 or 7 particular activities that try to get across some of the principles of computer science. Now, the objective here is not to have the kids really understand that at the end that they know what computer science is all about, but the idea is that they understand that there's a fun little idea, there's a fun concept, and be it a colouring activity or be it sort of running around or just realising that there's something interesting. The idea is to sort of get them to look at this again. And also the idea is that they understand that some quite deep ideas are actually very simple to understand, and that's why I'm trying to present these as games. Right? So if at the end you sort of say, well, yes, but none of these kids is going to be able to program, of course they're not, that's not the objective. In fact, there are no computers anywhere close to this activity. This activity is completely unplugged. Okay? So, so before we get on to the interesting piece, the fun piece, I want to tell you why is computer science important. So I guess, we're currently living in, I suppose, a country that used to be called Ireland. It's probably currently would be better named Ireland, I suppose, to some extent. And people are concerned about jobs and the economy and everything else. But, frankly, there is no recession in the software industry. And so if you look at, these are just things I pulled off the web today. In the US, software development, so I suppose the prime job that computer scientists do, is now regarded as the #1 job in the United States. So this is a quote from CNN Money. And this is a similar quote from the Careers Cast. And this is a survey to judge what is the best occupation across the entire world. And guess what? You might not see it. You see it here. Oh, wrong thing. Computer engineer ranks as the best job in 2011. Now, are there jobs? I'm going to flick very, very quickly through a whole series of announcements that the IDA made in roughly the last 12 months. So I'm not going to go through these in any detail, but the important thing is that when you look at these, you'll see that new jobs are being created. So Murex, PayPal, IDA, this is HP's Cloud Center, 50 new jobs. Guild, create 100 to 200 jobs. We have Accenture, who's opening an analytics lab up in Dublin. McAfee, 30 jobs here in Cork. Dell, they're building a cloud technology center. Ericsson are building an R&D center in Athlone with 100 new jobs. 60 new jobs in Symantec. PayPal, 200 new jobs. Major expansion of VMware, and it goes on, and it goes on, and it goes on, right up to the last few days, where this year, Accenture, just last week, Accenture announced 100 technology jobs, and there you go. Lots and lots of jobs, okay? If you look at the jobs that have been created in 2011, IDA have created approximately 13,000 new jobs, and of those, 47% of those are in the software or computing area. So this is why I tell you that computer science is important and computing is important. So, so there is no recession in software. Okay, so if you go to companies working in the software industry, what they'll tell you is that they just can't get the right people. So if you're advising a kid who's going through the CEO system, get them to choose computer science. They will enjoy it, especially if they're going to get 400 more points. The dropout rates that Willie mentioned earlier, once kids are 400 points or above, they just fly through the program. Okay, so what we're going to do is start with a magic trick. And so Kate's going to help with a magic trick. So, so let's, will we try it? You want to come? Oh, so what she's going to do, she's going to put 5 by 5 of these on the board, and then I'm going to turn my back. She's going to play a little trick, and I'm going to try and guess which one she's changed. There you go, 5 by 5 now. Okay. So which she starts. So I'm going to need some volunteers in a minute. So I'm going to need 5 other children in a minute. So there's 1. So what are kids? There's 2. There's 3. 4, 1 more, and 5. This girl because she's late. So, so if you all come down and sit in the front row for a few minutes, then I'll get to you in a while. Oh, you already sit in the front row. That's fine. So this young man here. If you sit over there beside that girl, this young man and this young man here. Good. How are you doing, Kate? There you go. Another one. Well, do you want to put this one for you? There you go. Right. Okay. You have 1 more row and you're done. So lots of things in computer science seem as if they're kind of magical, and they have a very simple idea behind them. And so at the end of the lecture, what I'll do is I'll explain how we did this little magic trick, and maybe some of the kids can try and figure out how I did it. So what I'm going to do is I'm going to add on a couple more of these. So I need some green ones. So I'm going to add on a couple more. So put another one there, put one here, put one here, put one here. I'm going to put one here. I'm going to put none there. I'm going to put a pink one here. I'm going to put none here. I'm going to put a pink one here. And I'm going to put a pink one here. Now what Kate's going to do is, while I have my back turned, she's going to take a pen, and she's going to lift one of these guys. She's going to mark it underneath, and she's going to change its color. So Kate, lift one up, change its color. So if it's green, make it pink, and if it's pink, make it green, and mark underneath with a little X or something. Are you done? No? Don't look. You done? So, which one did you change? Well, I think you changed that one. Magic. We'll come back to that in a while. Okay? So this is a very, very cute trick, which is very important. So come on over, Kate. It's okay. So, so what we're going to do first is talk about, well, how do computers represent binary numbers? So how to represent numbers at all? So, well, if some of you can figure out, well, what did I do here? We'll do a little quiz at the end. You can sit down for a sec. You can sit here. So how do computers represent binary numbers? Well, basically, computers use a 2-digit number system. So you have a 0 and you have a 1. So in school, you might have learned that as base 2. Every day we use what's called base 10. And we call these zeros and ones bits. And they represent, the reason we have bits is because they're useful in computers. They're represented by transistors. So how do we get, you might sort of say, well, being able to count from 0 to 1, doesn't allow you to count very, very much. So how do you get bigger numbers? Well, you get bigger numbers by using more bits. So 8 bits is what we call a byte. But of course, now you hear about computers that are 32 bits and 64 bits. And this means that they can represent bigger and bigger numbers. Okay? So how do we understand binary? Well, basically, any binary number is made up using a bunch of little dots like this, if you prefer to think it that way. So we have a bit representing a 1. We have a bit representing 2s. We have a bit representing 4s. We have a bit representing 8s, 16s, 32s, 64s, and so on. And if we want to make up a number, we just decide, well, which of these do we want to use? If we don't want to use them, we turn them over and call them 0. And if we do want to use the card, we turn it over and regard it as a 1. So if I could take my 4 volunteers, my 5 volunteers, you can all come up onto the board, come up here for a second. So you're going to help me with this, right? Great. So line up here for me, and you're all going to become bits. So Kate, you can help here because you're going to count the numbers to me. So since you're the smallest, you can go over here. So you're the 1 bit. So you hold your card. There you go. Hold that there. You're the 2 bit. So all stand beside each other. You're the 4 bit. You're 8, and you're 16. So how do we make numbers? Hold up your cards. So how we make numbers is that if we want to use the bit, then the children will hold the number out. So Roisin is going to hold out 1. If we didn't want to use the 1, Roisin is going to turn it over. And now we don't use that bit at all, right? So how does it work? If we want to make a 9, so there's a simple technique for 9. I'll show your bits. You're holding 16. Is 16, is that too big? If you want to make 9, is that too big? So turn over your card. What number are you?
8.
So do we need an 8 to make 9? We do? So, and so now we use a 1, right? Exactly. So you turn over your card because he said we don't need a 1 and we don't need a 4. We don't need a 2. And there you go. And what do we have? We have 9. And so what's the number?
0, 1.
There you go. 0, 1, 0, 0, 1. If you want to make up, so how do you make up, so do you want to make up, so how would you make up 3? So if we need 3, do we need 16? No. Do we need 8? Do we need 4? Do we need 2?
Yeah.
Do we need 1? Yeah. So what's the number? So what binary number is that? 0?
0, 0, 0, 1, 1.
Exactly. How about 12? Who's going to make, oh no, 16, because this guy's not going to get to turn his card. So make 16, or 19. Do we need 16? Yes, we do. So do we need 8? So 8 plus 16 is too big, right? So you leave your card turned over. 8 plus 16 plus 4, too big. 16 plus 2, do we want him? We want him, yeah. And so what's that? That's 18, and we need Roisin to give us 19. So what's the number? 1.
0, 0, 1, 1.
Perfect, great. So, and if I asked you so can you kids make up the number 10101? So you're 1, so you show your number. You're 0, you hide it. You're 1, you show it out. You hide it, and you show it out. What's the number? How do you get the number? You just count up the dots, don't you? 21, is it? Yep. Okay, good, good. Great, thanks folks. Is binary clear? Do you know how it works? There you go. Thanks folks. You can all sit down. So, so binary numbers, of course, you can represent numbers, but you can represent all sorts of other things. You can represent words, and you can represent other sorts of data. So, so imagine we had a little guy who was stuck in the building, and he couldn't actually get out for some reason. So, and all he had was, he was in this big tall building in the middle, and in every window there was a lamp. There was a Christmas tree in this case. And, you know, this little fellow on the left-hand side sees that, you know, there's a little computer person over there in the other building. So how do we communicate with that person? Well, he could figure out, well, with binary, I can encode a message. And if I am careful about which trees I turn on, that gives me a number. And a number could represent a letter. So 1 could be A, 2 could be B, 26 would be Z. And so if he wants to make up that message, he turns on the right Christmas trees. And so Kate, do you want to try and figure out what that? So Kate's going to help us figure out what that messages. So let me give you, have you got a pen? So tell us how you're going to do it. So use the binary, yeah. And this one is?
16.
How do you know it's 16?
Because this one's here.
So that's a 0, so you don't use that.
That's
1,
1.
so that's
That's 8.
8.
0, 0, 0.
So what number is that?
It's
8, so right, H. Okay, you want to keep going? So what's the number? 4 and 1, because you're using the 4 card and the 1 card, so you get an E because that's 5, isn't that what you said? Good, keep going. So what she's doing is just the trees represent 1s and the blank windows represent 0, and she's counting the dots on the card to figure out, well, what the number is. And then when she gets the number, she's looking up down here in the code to figure out, well, what does that number represent, and she's writing that beside it as she goes. Now she hasn't seen this, so see how it goes. So, okay. Of course, it's good for counting, doing your maths in your head rather than doing your maths in your calculator. Well, T. Come on, folks, what is it? What is it? What is it? Good. And the last one is 00100, which is D. And what's to say? Help, I'm trapped. Well done. Congratulations. Good job. Okay. So that's how you represent numbers. So we can represent letters. We can represent. So in fact, there's a code called the ASCII code, which works almost exactly the same as this. Unicode, which you might hear about, which represents words and digits. It all works on exactly the same principle. A number represents a character or a little mark. And you know, the computer, which in this case is Kate, has to figure out how to encode how to decode those messages. So this is done. You've come across this every day using, well, you may not use a modem anymore, but you use a fax machine. And what happens when you call a fax machine is you hear all these high and low sounds. All these high and low sounds are just basically representing the 1s, the high sounds, and the 0, the low sounds. And so this is the basis for communications. It's the basis for how CDs work and everything else. Let's talk about images. So once you can talk about numbers, you can start talking about pictures. And so hopefully everybody can see that this picture is the letter A. It's not a very high resolution A by any means, but it gives you an insight into how the computer actually represents letters. Okay, we have a display. And the display has pixels, has dots in it, and what we have to do is control which dots are on, which dots are off in order to figure out what the picture actually is. So each computer screen has a grid of dots. As I say, it's pixels. The simplest screens only have black and white dots, so ones that are either on or off. So you see, in fact, you see these in these sort of red displays that you see now with you know, for sale, whatever it is, or on the way home. Speed camera in operation or something. These ones that these are basically exactly the same thing. Either the light is on or the light is off. So by turning on and off the dots, we make the pictures that we want. And grayscale screens, so screens that have different shades between white and black. These are just, every dot here corresponds to a number. Where the number gives you an indication of how bright or dark or how white or black the image is. So I mentioned earlier on that a byte is 8 bits. There are 256 shades of black through to white, and so a standard monochrome display, every pixel has a number, can be represented as a number between 0 and 255. So if you've got color screens like your TV, they have millions and millions of colors. And so basically, any image that you see is represented as a set of numbers. And so the question is, how do you best do that? And there's no right answer. There are lots and lots of different ways of doing that. And in computer science, what you would do is study different ways in which you could represent those images and how you could play with them. So what we're going to do is look at a couple of simple little examples. So here's an example of an A, and what we could do is we could simply say, okay, the image is represented, we have 30 squares, and so we start from the upper left, right along, left to right, and from top to bottom. And we say, well, the first one is off, so that's a 0. The next one is on, that's a 1. The next one is on, that's a 1. The next one is on, that's a 1, and so on. And we keep on going. And we end up with 30 little bits, which we can figure out, well, what is the image? And we can color in the right ones, and that gives us the picture. That's quite laborious. And by laborious, I mean that it takes a lot of information to represent that. And so there's another style, which is instead of representing each pixel, each square as either a 0 or a 1, a white or a black, we can look at each row, and we can say that rows have particular patterns. And the pattern is always the number of white cells, then the number of black cells, then the number of white cells, then the number of black cells. And so the first line is 1, 3, 1, because we have 1 white cell, we have 3 black cells, and we have another white cell. So that's 1, 3, 1. The bottom one is 1, 4, because we have 1 white cell, and we have 4 black cells. This is 0, 1, 3, 1, because we have no white cells. Then we have 1 black one, we have 3 white ones, and we have 1 black one. Okay? So, if you were a computer, and Kate's the best approximation I have to one, if someone came along and said, well, and gave you this set of numbers, the question is, what is the picture that is represented underneath that? So do you understand what you're doing? So every row is, so this is the number of white cells, then the number of black cells, white, black, and off you go. So Kate's going to color that in. Now, of course, what we're doing here is pretty simple, right? Well, I hope it's going to be simple. We'll see what image comes out. But you might have seen people trying to make pictures out of, say, shells or pieces of pasta or pieces of card. Exactly the same kind of principle applies. We have an image where the numbers represent what the perfect value in that cell is going to be. So, for example, if it's blue, blue has a number. And you look into your box of shells, you look for the shell that has the right, as close a color blue as possible, and you put it there. Okay? And if you do that enough, you'll end up with a picture that roughly represents what it was that you're looking at. And so, so have you got 11? Yeah, okay, good. So we'll leave. So Kate's going to work away on that. So Kate, I'm going to turn off your light, and you're going to keep going, okay? So we'll see how she gets on. So, so this, while it's a simple idea, well, I hope you agree it's a simple idea. So we just count the number of white and black cells in every row. This is actually called run length encoding. It's a data compression technique. Now, of course, a 7-year-old, or in Kate's case, a 9-year-old, doesn't care that it's that's a data compression technique. It's a nice coloring problem. It's a nice little puzzle that they can sit down and they can figure it out. If you give them a blank grid and ask them, well, draw a picture in that and extract the encoding, these are important skills that you need in order to figure out, well, how do you design graphics and so on. So, good. So Kate's going to work away on that one and tell us what she comes up with. And there are bigger ones. If any of the kids here want to try some, I have some in my box. Anybody want to try some? No? You want to try some? So 1 second now. So you want to try one? Here's a big one for you. Since you're brave, where's he gone? And there's a fellow over there. So I might give those to those 2 fellows there. Yeah. And I'll give you some pieces of paper so you can see underneath. There you go. Great. So see how we get on, guys. So remember, the first number is a number of white cells, and then the next number is a number of black cells, the next number is a number of white cells in every row. Okay? Great. So human-computer interaction is not all about algorithms, and it's not all about representing numbers. Computer science is also about understanding how humans think. So you might have heard of the field of artificial intelligence. So this is understanding, well, how the brain works and how we can automate that to some extent. Now that sounds very grand. But it's also important when you're designing interfaces for computers. So I'm going to do a little experiment with the rest of you, and you all have to participate. We're going to do the Stroop test. So the Stroop test is pretty easy. What I want you to do on this one is we're going to call out the color in the word. Okay, so for example, purple, green, blue, orange, yellow, yellow, blue, green, orange. Okay, you all ready? Now you all have to do this, right? So all together, 1, 2, 3, purple, green, blue, orange, green. Good, 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 good. Okay, good, great, great, perfect, perfect, great. So here's a slightly different version. So now here what I want you to do is I want you to ignore the color, but I want you to shout the word. Okay? So it's purple, green, blue. Okay? So, and I want you to do it as fast as you've done it before. Okay? So 1, 2, 3. Good. Well, you finding it more difficult? Finding it more difficult, right? So what about this? So take the same thing, and now don't tell me what the word is. Tell me what color it is. Okay? So it's going to be pink. I suppose yellow, red. Okay. So you ready? 1, 2, 3. Not so easy, huh? Now, there's nothing wrong with your brain, okay? Are you done? Almost. Almost. You want to take a look at that line? Count again. So you're, that one? Count those ones, 4, 11. So there's nothing wrong with your brain. This is called the Stroop test. And the problem is that you're getting two totally different signals for how you should react to this, right? You're getting the color on one side and you're getting the word on the other. And some people find it easier to read the words naming the colors regardless of the color, whereas other people find it difficult to read the color given the word, okay? And, you know, there's lots of conclusions that, oh. Okay, we'll come back to that in a second, well done. We'll come back to that in a second, but this is a Stroop test, and really in computer science what we want to do, we want to know things like this. We want to understand what do people find difficult. So are particular colors difficult? When you lay something out, sometimes when you play with something at home, you just find it isn't natural. It doesn't kind of, you know, it doesn't sort of work for you. And this is the science of human-computer interaction, and we have to understand what that's all about. And this kind of game is kind of fun, right? Like you can, you know, a bunch of kids together will have a good laugh playing this kind of thing. It's a very simple test, but it's a very, very significant psychological test. So let's see how you did over there. So Kate got a teacup. Well done. Cool. Everybody see it? Yeah? Great. Thanks, Kate. Good, good. Well done. Okay, so running together. So you might have seen, you might have heard of, so everybody played hopscotch. This is a hopscotch-like game. It's basically the principle of this is that we want to sort numbers. Now, normally, if we were demonstrating this, we would draw a hopscotch size network, which I'll show you in a second. Something looks like this. Okay, so all the kids are standing over here. They all have a number, and they are all going to be in nice sorted order when they get out the other side. We call this running together because it only works if all the kids progress through the network at the same time. If one races ahead, the chances are the answer will be wrong. So the kids have to do this at the same time. And so in the full day event, we will have set up different copies of this, and there will be teams, and the objective will be for the teams to get the right answer and to do it as fast as possible. And so if they don't cooperate and do this together, they will probably get the wrong answer. If they get the wrong answer, they're disqualified for that round, and they'll win a prize when whoever gets the most right answers the fastest. So why is sorting important? Well, sorting is important because a huge amount of what we do in computers is sort. We have to sort the dates in our calendar. We have to sort the files in our documents have to be in sorted order. We might want to sort numbers in a spreadsheet. And that's a fundamental thing that we want to do. The other thing we want to, so as computer scientists, so as people who worry about, well, how computers solve problems, that is a problem, right? How do you solve this sorting thing? Now, there are lots of different ways of doing it. Now, how are we going to do it faster? We can all think of a naive way of doing it. Well, you compare everything and you sort of switch one around with the other one and so on. So how could you figure out a better way of doing it? That's a question of what algorithm do we use? What method do we use? So that's a really important question in computers, in computer science. We could figure out, well, is there a way of sort of thinking about the problem or representing it so that we can solve it more efficiently? And that's a data structure problem. And what this little exercise is all about is doing things in parallel. So is there a way in which we can make a big task easier by doing many things at the same time? So sorting network is a very simple example of how you might do this. Kate's thing is falling apart over there. So how does it work? Well, you have a bunch of numbers over here, or in our case, kids carrying numbers. And they step forward onto these circles. And so these two children will compare the number that they have. The one who has the smallest number will travel down this branch. The one who has the larger number will travel upwards. Okay? And you do that consistently at every circle. Okay? I'm not going to explain how it works or why it's the size, but it's very easy. It's very easy why. And at the end, what you have is no matter what order the numbers are on this side, they will be in sorted order on that side. And so Kate's going to demonstrate this with these are my card-carrying children, and there's your network. Do you want to turn on your overhead projector over there? So how does it work? Here you go. So I'm going to give you some numbers. There's a 2, so put a 2 anywhere you want. Anywhere you want. Here's a 4, put the 4 anywhere you want. This is high tech. Try to do this at PowerPoint. It's a nightmare. 289. 1. Need another one? Yeah, 422. So what Kate's going to do is she's going to push the numbers along, and at every circle we're going to do a comparison. And the small number is going to go this way, and the big number is going to go that way. So what happens here? So where does the 2 go? 2 is smaller, so it goes down. And okay, and now we need to do the next ones. So this will be done together. So all the kids will be running at the same time. Okay, and the 1 goes where? Down here. And here. The smallest number goes down. Good. And the biggest number goes up. And we do it again. So which of these numbers, so which is smaller, 1 or 2? 2 goes over here. Which is the smaller, 4 or 422. So the smaller goes down and the bigger goes up. Good girl. Which is smaller goes down and the bigger goes up. And do it again. So the smaller goes over here, the bigger goes up. The smaller, so the smaller one goes up. Yeah, good girl. Yeah. And so this smaller goes over there. Yeah, sorry. Good. And so the small goes down, the big goes up. Big one goes up. Are you right? Yeah. And so the big one goes up, and the small one goes down. There you go. Now, obviously, on a screen like this, it's not so exciting. But if these are kids running together holding these cards, and they have to do this together and as quickly as possible, it becomes quite a cute thing. And what they're really doing here is learning about how to do things in parallel. The method, the algorithm that's underneath this, and the thing on the floor is very important because that's really what puts the whole thing together. Okay? And so as a variant of hopscotch, it has its own value. It's quite a fun thing to do. Okay. So how does it work? Well, Kate's going to demonstrate it. Now, coloring. So how are we fixed for time? We're doing okay. So what's this all about? Well, this is actually a really interesting problem. Okay. It's fun because kids like to color, but from a computer science point of view, it has almost, there are people, believe it or not, who spend their entire lives, and in fact several generations of people have studied the problems that are underpinning this simple coloring problem. So what are we doing? Well, so you give kids a map, so a map of the United States in this case, and you give them a bunch of crayons, and you ask them, well, color the map so that any two states that are adjacent, that share a common border, have to be colored different colors. So for example, if Texas is going to be blue, then New Mexico, which is just above it, has to be colored something other than blue, okay, red or something like that. So you might sort of say, well, yeah, but you know, that's not really interesting. I just get my colors and I color. No. If you have a large box of colors, that's fine. But if you tell the children, well, here's 2 crayons, do that with 2 colors, or 3 colors, or 4 colors, then it becomes more interesting. Now, if you're doing this on the drive in the car, you need a lot of maps, right? So, so you know, this is the poor old cartographer. He doesn't get to buy very many cans of paint, and he has to color some maps. And so here's an example of a map. In the interest of time, I'm going to skip over the demo. So this map can be colored with 2 different colors. So this region and this region share a border, so they have to be different. But this region and this region don't share a border, so they can be the same color. And so this one can be colored using only 2 colors, which might surprise you. If I give you 10 colors, it's very easy. Here are other ones which are slightly more difficult, but these can be colored with 3 colors, and it's not obvious. And so again here, what you want kids to do is try to figure out what are the rules that help them to color these things. And again, there's a competition element. If you know this, if you know the bottom one here can be colored in 3 colors, who gets it the fastest? And in order to win this game, they need to understand some simple rules. And what most kids will figure out is that if they color one particular, so most kids will figure out that if they color one particular country one color, then you know, the neighbors can be all but that color. Really bright kids will figure out, well, hold on a second, there's one of these I need to color first, otherwise I kind of get stuck because I run out of colors. And you know, this is essentially these simple decisions. Which one should I choose next? Is actually an entire field of heuristics that has been studied for you know, tens of years. Okay, is this deep? Yes, it's actually very, very deep. So there's a bunch of games you can play. Imagine you've got 2 kids who are trying to color this map, and one is doing it properly and carefully, the studious one, so she's trying to use as few crayons as possible, but the other fellow doesn't care. He's just coloring as he goes, and he just makes sure that that you know, he doesn't violate that requirement that things that our neighbors have different colors. You know, there's some very deep questions around, well, how many crayons do you need? Nobody knows how many crayons you need. We know that if you've got 33, that's enough, but we don't know if 10 but we believe 10 are too much. Nobody has ever been able to prove that. If you have 2 maps, and a child gets to, and countries are paired from each map, and the question of how many crayons do we need to give the kids to color that? Nobody knows. Nobody has ever been able to figure out what is the maximum number of colors, crayons that you need to give that child. You might sort of say, well, you know, these computer science guys are pretty stupid, huh? So in 1852, there was a conjecture that every map could be colored with at most 4 colors. And it seems kind of obvious if you think about it, but it took, you know, 120 years for somebody to actually prove that that really was true. So, and that wasn't for the lack of trying. You might sort of say, well, you know, but who cares about solving these kinds of map coloring problems? Well, these problems are actually at so this particular problem is at the fundamental root of the entire field of computer science, which is which problems can you solve easily and which problems can you not. And just to give you an idea, imagine you had a 50, you could color So you could, had a computer and it could color 50, it could decide, well, how to color 50 countries in an hour with 4 colors. If you add another color, that computer would need 4 hours to do it. If you added 10 more colors, it would need a year to do it. This problem gets really, really, really hard as the number of countries grows. Now, quite often, so Kate would be able to solve one of these very, very quickly, but they get very, very hard. And this is so we don't need to go into what it means, but there's a fundamental question in computer science, which is, and I think it is the question in computer science: are there problems? Can all problems be solved efficiently? Can we solve all problems easily in a reasonable amount of time? And nobody knows. So the magic trick. So what did I do? So this is actually an example of, so that little trick over there, anybody figure out how I solved it? Any of the kids figure out how I solved it? No? No? So this is what's called, this is an error detection method. So, and it's really important because when you go into the bank, and you've probably often worried about this problem. You go into the bank and you hand over your 100 euros and you write down your account number and you pass it to the person behind the desk, and that person bangs in the number and says, thank you very much, there's 100 euros, see you tomorrow. And you're there thinking, well, hold on a second. How do I know that it went into my account and not somebody else's? So when you're in the supermarket and you pick up and you're buying your box of Weetabix or your bottle of milk, and the checkout thing goes beep, what does that mean? It means that what's going on when it beeps is that it's doing some error correction. And so it's like the computer says, that cash register says, well, I didn't quite read that properly, but I know what it is. In the bank, you don't need to worry about the fact that she might have made a little digit of a mistake, because the numbers are designed so that that doesn't matter. So how do we do it? Well, when Kate came up with these cards, she had 5 by 5, and she had some of them green and some of them pink. And what I did was I added some additional cards, and I did so carefully. I put my cards on the outside of this so that the number of pinks in every row and the number of pinks in every column was even. Okay? So if Kate had 4 pinks in the column, I put on a green. If she had 1 pink in the column, I put on a pink. Okay? So once she has decided how she's going to lay out her 5 by 5 design, then what I did was I made sure that all of the pinks were even. And then when she came along and flipped over one of her cards, she was acting as if she was a Tesco scanner working incorrectly. Then I could see that, because if she made a pink one green, then my even on the rows and columns didn't work anymore. If she made a green one pink, it also didn't work anymore. And so this is really what's called a parity check. There's a joke in the picture, a parity check. And so this is the fundamental method. And this if we didn't have this kind of error detection, communications, finance, security, we could not rely on them. It's a very simple idea. It's a cute little trick to play, but it has really a very, very rich and deep feel behind it. So there's no reason why anybody should be worried about this sort of stuff on error correcting codes. It's very, very simple. Okay. So what about using a computer like? So this is supposed to be computer science. I'm not going to go into programming. If your kids are interested in programming, what I would highly recommend you look at is a system called Scratch. So Scratch is built by MIT. It's a really simple to use jigsaw-like way of building programs. And these programs can give you games, music, art, whatever. It is really, really simple to use. It's completely free. Just Google Scratch and MIT and you'll find it. I'm not going to do anything with it tonight. So if there were computer scientists in the room, of which there are some, you'd say, well, you didn't really tell us anything about algorithms. And I didn't. So what I'm going to do now is tell you all about algorithms through a simple story. Now, it's a bit out of season, but hopefully the idea will become clear. So kids like learning things through stories, And this is a story that tells how to do what's called why a divide and conquer algorithm works. Okay? So, Santa's dirty socks. 'Twas 10 of midnight on December 24th, and all was not well in the far, far north. Some little elves were wrapping 1,024 toys, roller skates for 1,024 good girls and boys. At 10 to midnight, the elves called Santa Nick. Tonight, all the boxes had been filled extra quick. St. Nick was thrilled. Right then, fill up the sleigh. 1,024 boxes, and we're on our way. Then Mrs. Christmas burst through the doors. Where are your dirty socks, Santa Claus? A young elf cried, Santa, I dropped your dirty socks into one of these 1,024 boxes. Quick, unwrap every single box. I'm not leaving till I find those socks. Sorry, Santa, said the supervisor elf. Us workers are all union. We'll finish at 12. Said Santa, no need to be unpleasant. I've got a big pair of scales, just weigh each present. They all weigh the same, and when you put them in the bucket, each bucket, except for one, and that one's the culprit. With all due respect, replied the supervisor elf, it'll take a jolly long time, and you can do it yourself. If we could make one comparison every second, we'd be here till 12:07. A little elf piped up, I've got an idea. We'll just need to use divide and conquer here. Put half of the boxes on that scale and half of the boxes on this. Whichever side goes up, this pile we dismiss. The supervisor elf, with an unimpressed gaze, pointed out, we'll still be here for days. You've narrowed it down to 512, hardly any help from this little elf. Wait, said the elf, only beginning his campaign, watch what happens when we have it again. So he halved it again, and now their fix was narrowed to 256. Then after the third comparison of weight, their problem was reduced to 128. Then 64, then 32, 16, 8, 4, 2. It's true. On the 10th comparison, with much joy, the elf found his erroneous toy. A job that could have gone well beyond time limits took just a matter of minutes. So the gift was replaced, the elves went home, and Santa set off on his worldwide roam. No poor child, far or near, will have to smell Santa's dirty underwear. But first the little elf was approached by St. Nick. Where did you learn that clever trick? The elf replied, on magic I make no reliance. All I needed was a little computer science. The end. Thanks very much.